এই
হ্যাঁ
একদম 6টায় শুরু করে দেবে, হ্যাঁ রিলেই।
আমি এখানে গোয়িং লাইভটা দিয়েছি, দেখো ইউর লাইভ দেখাচ্ছে। হয়ে গেছে বোধহয়, দেখো লাইভ, মানে খুব একটা লেট হচ্ছে না।
স্ক্রিনটা চেঞ্জ করো, মানে গুগল মিটের স্ক্রিনটা।
হুম এটা পুরোনোটা দেখাচ্ছে,
এটা ওবিএস এর স্ক্রিনটা দেখাচ্ছে, ওই গুগল
আমি দিয়ে দিয়েছি চেঞ্জ করে দিয়েছি।
আচ্ছা এখানে দেখাই না।
সাউন্ডটা একটু চেক করতে হবে।
সহিত
হ্যাঁ হ্যাঁ স্টার্ট করো।
ছটা শুরু হয়ে
হ্যাঁ
স্যার এসছেন?
হ্যাঁ স্যার এসে গেছে।
স্যার?
স্যার অনেকক্ষণ আগে এসছে।
ও আচ্ছা। কিন্তু এর পার্টিসিপেন্ট নেই তো, নেই তো, সরি, অডিয়েন্স খুব কম তো।
হ্যাঁ অডিয়েন্স কম, ঠিক আছে। আচ্ছা অডিয়েন্স তাহলে আরও 5 মিনিট দেখি তাহলে।
মাত্র 11
এদিকে 11, ওদিকে 30 মতো আছে।
ইউটিউবে।
হুম 35। চলো 5-এ স্টার্ট করি।
সহিত
হ্যাঁ স্টার্ট করে দাও।
সহিত
হ্যাঁ স্টার্ট করে দাও। হ্যালো।
হ্যাঁ
হ্যাঁ স্টার্ট করে
স্যার,
দাও।
স্যার সহিত
স্টার্ট করো।
কোথায় গেলেন?
হ্যাঁ
স্টার্ট করুন
স্যার
স্টার্ট
হ্যাঁ
করুন
শুরু করবো।
অলরেডি লেট করে ফেলেছেন 5 মিনিট
হ্যাঁ হ্যাঁ হ্যাঁ
স্টার্ট।
Good evening. Very warm welcome to all of you to today's webinar organized by Department of Mathematics and Physics. Today we have with us Dr. Wasiur Rahman Khudabak. He is doing his postdoctoral research at Mathematical and Bioscience Institute at Ohio State University, USA. He completed his PhD from Technische University Darmstadt, Germany, and he did his master's from ISI Kolkata. He will be talking on dynamic survival analysis of epidemics and how COVID-19 shaped it. A very interesting topic indeed. Hope we will learn a lot from him. First of all, on behalf of the organizing committee, I would like to thank Dr. Khudabak for giving us the time out of his busy schedule. Now, I would like to request our Vice Principal, sir, to formally welcome the speaker and inaugurate the session. Sir, now it is over to you.
Thank you. Good evening, everybody. Respected resource person, honorable dignitaries, dear colleague, research scholars, organizing committee conveners, joint conveners, and affectionate students. It is really a great pleasure and privilege to be present in the international webinar organized by Department of Mathematics and Physics in collaboration with IQAC. Being the head of the institute, I must congratulate the teachers of the Department of Mathematics and Physics, especially Dr. Mohammad Saifuddin and Professor Somu Saha, as they have taken initiative to organize the international webinar. First of all, I, on behalf of the institute, must welcome the respected research person, Dr. Wasiur Rahman Khudabak, President, postdoctoral scholar at the Mathematical Biosciences Institute at the Ohio State University, USA. I would be immensely grateful as he has responded to our invitation despite his busy schedule. I convey my best wishes to our governing body president, Dr. Sudip Torai, and the all governing body members for moral support to organize the international webinar. I freely and frankly express my pleasure that we have got some highly energetic and enthusiastic faculty members, and they have been trying their level best to arrange various thought-provoking seminars on the virtual platform. I do hope that our participants would reap a sound harvest from the day's discussion. I firmly believe that this kind the day's discussion will be interesting and interactive one. The survey of the day's speech and reciprocal discussion, I do hope would further illumine the minds of the teachers and thought. I wish a warm success of the day's webinar. Once again, thanks to all.
Thank you, sir, for the welcome address. Now I would like to request Dr. Wasiur Rahman Khudabak to start his talk. Before that, a small announcement for the audience. So, audience are requested, please mute your microphone and off your video. Also, you are requested not to press on the present now button while the speaker is presenting. And another thing, at the end of the talk, there will be a discussion session. So during discussion, you can directly ask questions to the speaker, or you can drop your queries or questions to the chat box, which will be addressed by the speaker. So I hope that the audience will cooperate with us. Thank you. So now I'd like to request Dr. Khudabox to start your talk.
Uh, Good afternoon, everyone, or good evening, or good morning, depending on where you are. Yeah, it's an honor to be presenting to such a large audience there. I'm very happy to share some of the recent work that I've been doing here at the Ohio State University at the Mathematical Biosciences Institute, and some of the work that has to do with the COVID-19 pandemic. So. And I would like to thank the organizers particularly for organizing this and inviting me to present. So let me start sharing my my screen.
সাউন্ড আসছে না তো সাউন্ড আসছে না সাউন্ড আসছে না
Okay, can you all hear me now?
Yeah, you are audible.
Okay.
You are audible.
Okay. Yeah, I heard somebody saying that the sound is still.
Yeah.
Okay. Yeah. So can you all hear me well and see my screen? Okay.
We can't see your screen, but we can see you only.
Oh, okay. Presentation video. Okay. Let me stop processing. Start. How about now? Can you see the presentation screen?
No.
Yeah.
Please press on the present now icon.
Yeah. No, I did that.
Yeah, it's showing.
Okay. Okay. So yeah. So the talk is about dynamic survival analysis of epidemics, and then how COVID-19 shaped it. So a couple of weeks ago, when Saifuddin first contacted me regarding this webinar, and we were discussing the kind of topics that I could be talking about. So I as far as I can remember, I gave him a couple of options. I thought since it's going to be predominantly a math and physics audience, so I could probably talk about stochastic processes or something in applied probability theory, a little bit more technical. And I also talked about, I think, mathematical biology. And among all these topics, Saifuddin showed the greatest amount of interest in mathematical biology, and I can totally understand why that would be the case, because it's probably because the ongoing pandemic, COVID-19. So, and because I have been involved with a lot of COVID-19 modeling and response modeling team as part of the response modeling team at Ohio State University, working with the state government here. So I thought maybe it's a good opportunity for me to share what I have been doing and how, in general, one could go about modeling epidemics. So this is what it is all about. So the basic question that I would like to address towards the beginning of the talk is, how do you model an epidemic, right? Or a pandemic like COVID-19? And so that's going to be the premise of what I'm going to talk about. One thing that I would like to mention at this point is I'll try to be as lucid as possible. Some of the things are a bit technical in nature, and I would very much encourage if you pose your questions in the chat section, and if you let me know if I'm going too fast or if some things are unclear. I think everybody would benefit if things are clear. So Yeah. So the question is, how do you model an epidemic or a pandemic like COVID-19? And to answer that, I mean, many of you have already maybe studied a little bit of mathematical biology, mathematical epidemiology, and you probably already know that this is not a new field of science. It has been there for a very, very long period of time. In fact, one of the first works in epidemiology could be this one by John Grant in 1662. So what he did was he created this bills of mortality in the city of London. So it's called Natural and Political Observations made upon the bills of mortality. So that was one of the earliest works in epidemiology. It was not necessarily a mathematical modeling work, but it still had flavors of what we do even today. The first mathematical work was actually done by Daniel Bernoulli. If I'm not mistaken, he could have been a lawyer, and he was interested in calculating the increase in life expectancy if smallpox could be eliminated as a cause of death. So the thing was life expectancy was low, and a part of the reason was that there was a smallpox. So he wanted to calculate, okay, what would happen if we could actually eliminate smallpox. So it was a fairly mathematical work done in 1760s. Then in the later part of history, people came up with what are known as compartmental models, and they were first proposed by public health physicians actually. So what are compartmental models? I think by now, thanks to the media and unfortunately because of COVID-19, I think almost all of you probably know what compartmental models like SIR models are. So you have a population and you compartmentalize it in the sense that you say, okay, each individual belongs to one of the few compartments, like either he's susceptible, and in which case he belongs to a susceptible compartment, or he's infected and then he belongs to an infected compartment, or he's totally recovered or removed, or then he is in a different compartment. If you already have a vaccine, then you might be able to give vaccine to a proportion of your population, in which case that's an additional compartment. So it's basically a collection of compartments, a collection of sets that you are interested in. The first such model was actually done by public health physicians, and later Hamer in 1906 proposed a mass action model for the spread of disease. Now, a few words about the mass action model. So what does a mass action model mean? So mass action model, and to give you some context, I mean, a lot of this work and a lot of science has benefited a lot from physics. So mathematics and chemistry and even biology, they have learned a lot from physics. So mass action models were first used to describe the motion of molecules in gaseous molecules, so gas molecules basically. And the idea is, if you have gas molecules, from the perspective of a single molecule, they can really interact with any other molecule in a chamber of gas. So there is no limitation as such. They are moving around freely. It's a uniformly mixed population of your gas molecules, and they can just interact with anyone else. It's a pure random uniform mixing scenario. In the earlier days of mathematical epidemiology, a kind of similar model was proposed, where you have an infected individual, and you assume that infected individual could infect potentially anybody in the population. So it's like this gas molecule thing. So that's what is called mass action. So an implication of this is that the rate at which the spread of the disease would work would be proportional to the number of infected individuals, as well as the number of susceptible individuals. So if there are 5 infected individuals and 10 susceptible individuals left in the population, then the rate at which the disease would spread will be proportional to 50, for instance. I mean, the product of these two numbers. So that's a very naive way of modeling the situation, and it's probably not very realistic. But remember, this is as early as 1906. And then later, Ronald Ross gave the notion of basic reproduction number. That's also something that you probably have been hearing a lot, thanks to the media. And unfortunately, because of the COVID-19 situation. So it was in 1911, and he calculated this basic reproduction number in the context of malaria. And if I'm not mistaken, it was actually Kolkata. So I'll tell you a little bit about basic reproduction number later, but it's one of the key quantities in mathematical epidemiology. And then the first formal compartmental model was actually described in the series of papers by Kermick and McKendrick, so between 1927 and 1933. So again, as you can see, it's almost 100 years old. And the models that Kermick and McKendrick proposed 100 years ago are cornerstones of modern epidemiology. So these are now included in undergrad studies in mathematics and in physics and in epidemiology. Unfortunately, Kermick and McKendrick proposed a number of models that were, and also gave a few special cases of their models. So they proposed what are called renewal models. And then as a special case, they said, okay, if so-and-so conditions are satisfied, then you can actually reduce those renewal models into what are known as ordinary differential equations. So those are much easier objects to handle analytically. They're easily solved and things like that. And for some reason, people really caught on to this idea of ordinary differential equations. And 50 years down the line, now people think that the Kermick and McKendrick model is actually the ODE model, but it's not. The ODE model is actually a special case of the model that they proposed. So their contribution was actually much bigger than the ordinary differential equations. So it's kind of funny. And people went on to propose generalizations of the ODE model, and even those generalizations seem to be a special case of the original model. So yeah, we have been reinventing the wheel. So if anybody who is interested in learning a bit of mathematical modeling or in the context of epidemiology, I would highly encourage them to actually read Kermick McKendrick's paper, even though they're very old, but they have some really nice ideas. And in general, I mean, this is not the most recent survey, but this is still lucid enough and covers a lot of ground. So this survey by Fred Brower, a Canadian mathematician, he has written a lot of papers in mathematical biology, and he has this review paper in infectious disease modeling in 2017. That's a good resource for anybody who's interested in mathematical modeling and epidemiology. So when we talk about modeling, there are like various ways of modeling. There are various schools of thought. A particular school of thought or approach inspired by physics mainly is what is called mechanistic modeling. So what's mechanistic modeling? So mechanistic modeling actually relies on hypothesis for causal mechanisms. So when you see something, for instance, a dynamical system or any system for that matter, and you create some hypothesis like, okay, this is what is causing this thing to do or behave that particular way. So those are called mechanisms. So you create some hypothesis for causal mechanisms, and then you have some parameters to describe that mathematically, and usually those parameters have a physical meaning. For instance, in case of epidemiology, we can assign infection rate. So this is the rate at which an infected individual is trying to infect others. So they have a physical meaning. And the other, it's repeated, but the thing is, it also helps you to validate or try out different scenarios, like what would happen if some things are changing, if you make some changes in mechanism. For instance, in the case of COVID-19, we had a lockdown, and then people were encouraged to practice social distancing and to wear masks and things like that. And those are like behavioral changes. So in order to test what would happen if certain things are implemented, then mechanistic models are a good place to start. The other kind of modeling is statistical modeling. Statistical modeling, as you can imagine, is heavily inspired from statistics. It typically requires large amounts of data to reliably calibrate your parameters and for make predictions. A lot of those methods are based on what are called the laws of large numbers and central limit theorems. If you are familiar with a bit of statistics and maybe probability theory, the good thing about statistical models is that it allows you to estimate uncertainty in your predictions. In the sense that whenever we have a model, we estimate the parameters based on, let's say, data that you collect from India, from elsewhere, from USA, Germany, Australia, anywhere, and there's always a bit of uncertainty in those predictions or in model calculations. So statistical modeling gives you a way to estimate uncertainty in your predictions. So that way it's a very good thing to have. Now, could there be an approach that utilizes both? Well, perhaps dynamical survival analysis, and we'll see how that utilizes both approaches, where you have a mechanistic component as well as a statistical component. So that was a very long intro to what I was going to talk about. So sorry about that, but hopefully this puts you in context and gives you some background of things. So the other aspect, now going a little bit deeper into what dynamical systems have to do with survival analysis. Now, whenever we do modeling, as I said, there are two different approaches to modeling. You have a mechanistic approach and a statistical approach. In one approach, you prescribe mechanisms, in the other approach, you prescribe probabilistic laws or statistical distributions for things. Now, whenever you are trying to do modeling, you also have a question that you need to answer regarding what would be the basis or the minimal unit of your model. So are they individuals, or are they going to be population? Are you going to model at the individual level, or are you going to model at the population level? So if you're modeling at the individual level, which I call the micro scale on the left-hand side here, what you do is you assign probability laws to each individual, and then you try and see how you can generate likelihoods for individual trajectories. So what are individual trajectories? So suppose you pick a person like me at random, and then you check my status over a long period of time. So I'm susceptible, and at some point I get infected. I'm still infected, and then I get recovered, or I die, and then I change my status. So this is an individual trajectory. So you try to assign a likelihood function to individual trajectories, right? And then there's the other scale, which I call the macro scale, which is the ecological scale. So there, you forget about individuals. You're concerned about the whole population at large. So you say, okay, in this population, let's say India, and let's say we're talking about COVID-19. You say, okay, in March we had that many cases. And then in 1 week we had that many cases, and then in 2 weeks we had that many cases, and we saw this exponential growth. Now, how does the future hold for us? What is it going to look like in a month? So now, when we're talking about this thing, we are not necessarily talking about a single individual, right? We are talking about the whole population. So that's the ecological scale. And how do you model the whole population? Well, as I'm pretty sure most of you have already seen a number of ordinary or partial differential equation models that describe the whole population. Now, these are two different scales. I talked about the micro scale and the macro scale. Now, how do these two scales match up, or how do you move from one scale to another? So now, when you have the micro scale, these individuals, it's very easy to move from the micro to the macro scale. How do you move that? So you have your individuals. So if I sum up all my individuals, if I aggregate them, so we have these compartments. If we now think of the compartments themselves, we aggregate and then we assume the population is large and so on. So it allows us to take some limits. Then we end up at the macro scale. It's very easy. India is composed of, it's people. So that's very easy. Now the question is, how do I move back from the macro scale to the micro scale, right? So if I have the population, if I know India, I know how the trajectory looks like for India. Now, if I pick a random individual or a random Indian living in the city of Kolkata, for instance, and if he is susceptible to today, what is the likelihood that he will be infected in 2 days or so? So now we are talking. We have knowledge about the population, but we want to know about the individual. And this survival dynamical system distribution. This is basically one of the Ohio State University and Greg Impala at Ohio State University for the network model. The main driver of the project was a colleague of mine called Caleb Bastian from Princeton University, Yuhan Pan, a wonderful student at Ohio State University, and again, Evan Kana and Greg Impala. A lot of the modeling that we have been doing for the state of Ohio, the state government, there was a huge, a gigantic collaborative effort, and a lot of people from different departments of Ohio State University contributed to that. Joe Tien from the math department, Evan Kana, Greg Impala, Elizabeth Root from geography, Mark Weir from risk practices, Susan White from the medical center, Christina Lisinewski, Courtney Hebert, Stan Lemishaw from biostatistics, Hardy Fossler and Yuhan Pan, again, wonderful students. And of course, our state partners, the Ohio Department of Health and Ohio Hospital Association. So this has been a gigantic collaborative effort. So whatever good things that come out of this talk should be attributed to them, and whatever bad things that come out of this talk should be attributed to me. So in other words, views expressed in this talk are solely mine, and they do not represent the official views of any of our state partners or any of the funding agencies. All right, so now a bit of the McCormick-McKendrick SIR model. I'm sure you are familiar with it, but since we have a very wide range of interest here, hopefully, and the audience is broad, so I'll give a brief introduction to what the SIR models, the SIR model is. So you have individuals in one of the three compartments. The compartments are susceptible, infected, and recovered. Susceptible individuals become infected through contact with infected individuals at a given infection rate. So talking about parameters that have a physical meaning, that's one of those parameters. Infected individuals, they recover at a given recovery rate, and then recovered individuals cannot be reinfected. And I'm just saying recovered, but you can also think of them as removed. For instance, people who die, they cannot be reinfected, or they cannot infect anybody else. So from a mathematical modeling perspective, recovered and removed, you can put them in the same compartment. Just to be a bit more concrete than that, a very naive way or a basic way to describe the dynamics is to use what are called the ordinary differential equations. So you have three basically quantities of interest. So ST is the proportion of individuals in the susceptible compartment, and then this IT is the proportion of infected individuals, and RT is the proportion of recovered individuals. And what this tells you is that the proportion of susceptible individuals, they decay exponentially, and the decay rate is just beta, which is the infection rate or hazard function. We'll see how that pans. And the infected individuals, of course, when a susceptible individual gets infected, he moves to the infected compartment. So you have the same rate here, but once you get infected, you also recover. So you have a recovery rate gamma, and then you recover, and the recovered individuals stay recovered. So that's recovery rate. And a typical trajectory looks like this. So this solid blue curve is susceptible. So on x-axis you have time, which is denoted by t, and on y-axis you have concentration or proportion. Right? Concentration comes from, as I said, physics or chemistry. These are mass action type models. So that's where the nomenclature comes into play. So S is the proportion of susceptible individuals. As you can see, the decay here, over time. This dotted red line is the infected curve. They increase for a while, they hit the peak, and then the decay. And why do they decay? Well, they increase for a while because you're infecting more and more individuals. And then after a point, there are two things happening here. So there are not enough susceptible individuals left that you can infect, and the infected individuals also recover. So that's the reason they start decaying after that. And the recovered individuals just, it's a cumulative curve, so it just increases. Now, a bit about the reproduction number. So what's the reproduction number? Well, the basic reproduction number, or sometimes it's denoted by R0, is the expected number of cases directly generated by one of the infectious cases in a fully susceptible population. So let's say you go into a movie hall, everybody is susceptible, and one infected individual goes in there, and then he just randomly moves around. So how many cases do you expect? How many cases of new infections do you expect? So that's the basic reproduction number, very roughly speaking. Of course, in modern epidemiology, the definition has changed a little bit, and there is a little bit of nuance there, but overall, that's pretty much the same. And then there's one more thing called the effective reproduction number. Okay, so the effective reproduction number describes the number of cases generated in the current state of the population, where you don't have one single infected individual, but many infected people, many susceptible people, and that's it. So yeah, and in general, the crucial thing is that if the reproduction number is greater than 1, then you expect a large outbreak. If not, the disease will die out, and you wouldn't see a large outbreak. So that's the bottom line. I highly encourage you to go to this site. I'm not sure if we'll have time to go there, but if you just go to rt.live, you will see, for instance, these effective reproduction numbers over time for COVID-19, and you'll see how this has been above 1, and it has come down to 1, below 1 also. So if it's below 1, then you're happy because you have controlled the epidemic. If it goes above 1, then not so much. So for the students out there, I would very much encourage you to have a look at this website. They have described the methodology, and it's mainly for the cities and the states in the United States. But it would be a fun project for you to actually implement it for wherever you are. So if it's in India also has a very good database. I mean, so you can use that and do that. So that way you will also learn a bit of mathematical epidemiology hands-on. All right. So now the kind of models that we talked about are the models like the Coleman-McHenry model. They are a population level model, right? So we are talking about proportion of infected individuals. So this is a macro scale model, but it's not really difficult to arrive at from a micro scale or from a micro scale description, right? Where you describe individuals. And yeah, so we can hopefully then move back from the micro to the macro. We'll see how that's done. So now modeling at the micro scale. Is there any questions so far? Okay. Seems like there is no question, so okay, we'll just move ahead. Okay, so now we try to model at the micro scale, at the individual level, or sometimes it's called agent-based modeling. So what you do is you have, let's say, you assume you have n susceptible individuals and m infected individuals. Okay, so this is what you start with. So typically, you will have only one infected individual, and then you want to understand how the disease progresses. So, and then for the ith individual, you say, okay, I have this variable, this function, si of t. This is 1 if he or she is susceptible at time t, and 0 otherwise. Okay, so it's just an indicator function. I'm sure everybody in the audience, especially if you have a math or physics background, you're familiar with such kind of functions. It's just I mean, for mathematicians, this is a stochastic process, taking value between 0 and 1, and also from physics, you can just think of it as an indicator function varying over time. Similarly, define II and RI. So what it's doing is it's basically giving you some indicator functions for each individual, like which compartment they are in, what is their status, are they susceptible, infected, or recovered. And in the beginning, you can assume a Markovian setup for simplicity. So what does a Markovian setup mean? So Markovian setup is just a mathematical construct where you assume that future depends only on the present, not on the past. So conditional on the present information, you don't need to keep track of the history. Okay, so what that means is if I know that presently in the population there are 1,200 infected individuals and 1,500 susceptible individuals, so that's the information that I need to know to predict what will happen next. Okay, not the information like how many infected individuals were there last week. So that information is independent. So that's a Markovian setup. When you have a Markovian setup, you can use what is called a random time change representation. This is you don't have to go into the technical details of how you can write those equations, but all I'm saying is, or the key takeaway from this slide, if it's too technical, is that for each of those indicator functions, which were indicating whether or not a person was infected, whether or not he was susceptible to recovery, they would have trajectory equations, so they can be described in terms of some processes. So that's the probabilistic description of each individual. So these yi's, so si0, so this is the status at time 0. So what was the initial status? That information, and then at time t, if something happens, then it will switch. So it's I'll be happy to talk about it in greater detail if anybody is interested. But this yi's and zi's are unit rate Poisson processes. So that's again a mathematical construct that one can use. Bottom line is you can describe those individual level processes precisely mathematically. Okay. There's one more way of actually looking at this, which is called the Selke construction. So what is the Selke construction? The Selke construction says, okay, I'm still talking about individuals, and for each individual, I assign a threshold, which is exponentially distributed with mean 1. Okay, so everybody has a threshold, given threshold, and then I'm calculating the cumulative infection pressure in the population. So I'm saying, okay, so if there are more infected individuals, this pressure will be large. If there are fewer infected individuals, so this pressure will be small. And then I'm saying a susceptible individual will get infected whenever this cumulative infection pressure in the population is larger than his individual threshold. Okay, makes sense. So you say that, okay, I'm planted in this population, I'm in this population, and I'm surrounded by a lot of infected individuals. As soon as, and they're exerting a pressure on me to get infected. As soon as that pressure exceeds my threshold, I get infected. So that's the self-reconstruction. Pictorially, you can think of it this way. So on x-axis, we have time, and on y-axis, we have these individual thresholds. Now we have ordered them in ascending order. So this is the smallest of all the infection thresholds, the second one, and the third one, and so on. And suppose we have only one infected individual. So this cumulative infection pressure is basically then a straight line, this integral, because if you just have one straight line with slope just beta. As soon as this straight line crosses this individual threshold, you get one more infected individual. So now you have two. So it increases the slope here, and then it goes on, and then somebody recovers at this point. So then you decrease the threshold again. And then again, you reach the second threshold. So now, which means the second, you will have a second infection now. And then it goes up, and then the third, second recovery, and so on, and then you go on. And then you have the fourth recovery here. And then at that point, you don't have any more infected individuals. So everybody has recovered. So this will just remain stable at this level. So it will be flat. It will be flat, and there will be no more infections. So the infection has just died out. Okay, so that's the self-reconstruction. Again, mathematically, what does that mean? I'm sure a lot of our maybe students from the math department will appreciate the fact that you can actually precisely write down the probability of getting infected. So the probability that an initially susceptible individual will remain susceptible till time t. So what's the probability that I can escape infection for 15 days or so? This probability, given the history of the process, is nothing but e to the power minus a n t. So this was the cumulative infection pressure. This is nothing but an exponential probability. Okay, so this probability, of course, decays exponentially. So that's the bottom line of the self-reconstruction. And also this is the whole of, let's say, agent-based modeling. Okay, and in the simplest form, of course. Now, how do I move from the micro to the macro scale? So let's say, okay, as I mentioned, at the micro scale you have individuals. At the macro scale, what you want to do, you put them in compartments, and then you talk about the compartments. So what are the compartments in our case? We have S compartment, susceptible, I compartment, and R compartment, right? And so I'm interested in population counts in those compartments. I no longer look at individuals, I just look at the counts. And again, thanks to the Markovianness of the process, you can write trajectory equations using Poisson processes. But yeah, so you don't have to, again, using this random time change representation, but we don't have to go into the details of how you get there. If you're interested, I'll be very happy to talk about that. But in the interest of time, let's say the bottom line or the key takeaway from this slide is that just the way we did with individuals, we can also do the same thing with population level counts in terms of stochastic processes that are known as Poisson processes. Now, the other thing that I mentioned before is that when the population is very large, then you have smaller stochastic fluctuations. So when you have only one or two individuals or very few individuals, then you see a lot of stochastic fluctuations. So in terms of outcomes, you see a lot of different possible outcomes. The disease might die out very quickly. The disease might infect, I don't know, 2 people or 10 people or something like that. So you see a lot of different behaviors or potential outcomes. So there is a lot of fluctuation. But when the population is very large, then what happens is, and if you have a significant proportion of them infected, then except for maybe the very beginning of the epidemic, you see fewer or you don't see that much of a fluctuation. So the trajectories look more and more deterministic, which is to say that if I scale my counts by let's say the population size, this n was, you remember, this was the size of the susceptible individuals initially. If I scale by this thing, then the stochastic process actually converges to the solution of the ODE system, the ordinary differential equation. So it's a delicate probabilistic argument, but you can show that the fluctuation basically vanishes in the limit. You get something totally deterministic, and the ODEs that you get are precisely the ODEs that you saw in the Kermit-McHenry model. So now all of a sudden you see that these two modeling approaches are 100% compatible with each other, in the sense that if I take a large population limit from my agent-based model or the micro scale, I end up with what exactly is prescribed for the population level scale. So there's no mismatch, and so we are happy because things are the way they should be. So that's good to know. The other thing that we should now try and observe is that I have this system of ordinary differential equation. If I solve them partially, I can rewrite this as follows here. So what you see on the right hand side here. So in particular, ST, which was the proportion of susceptible individuals, can be expressed as e to the power minus beta integral from 0 to t I mu du. And if you remember what the infection pressure was, you will immediately notice that this quantity inside the exponential here is nothing but the large population limit of the total infection pressure. And this e to the power minus this limiting infection pressure was nothing but the probability of remaining susceptible till a particular time that we learned. So all of a sudden, what we see is that this ST, of course, it describes the proportion of susceptible individuals in the population at time t, but also describes the probability of remaining susceptible till time t, given the history of the process, which in this case, in the limiting case, it's the unconditional probability actually. So this is of course, a dynamical system, but also describing a survival probability, a survival function. So if you have taken statistics courses, then you will immediately see that this is the survival function of a probability distribution. That's the crucial observation. Similarly, if you solve IT partially, then you can forget this term for the time being. But if I show the other term, so we have this S dot. So if this is a survival function, minus S dot is a density function, a probability density function. If you have taken a bit of statistics or mathematics, you know that this is a probability density function, and this quantity e to the power minus gamma t minus u is again the density function of the exponential distribution. So what happens when you multiply two density functions in this particular way, so SU and then this, and integrate, and then this thing is nothing but the density of the sum of two independent random variables, right? So what that means is that again, that this IT is a density function because it is describing the sum of two independent random variables here. So one of them has distribution SU, and because we have a product, so that's independence, this is NA, and the other one is exponentially distributed. So that's the crucial thing. So pictorially again, we saw this picture before. This was the curve for susceptible individuals. This is the curve for infected, and this is for recovered. But now we have a different interpretation, and that's that this is a survival function, this is a density function, and this is a cumulative hazard. So, okay, that's the survival dynamical systems interpretation. So you have a dynamical system, you can transform it into a survival dynamical system that describes not only the dynamics of something, but also describes probability distributions. Okay, so that's the basic idea. You can have a look at the paper in Interface Focus. It's open access paper, so you don't need any institutional access for that. You can just download the paper and read it. And also for numerical implementation So there is a Python package that we developed, and this is also freely available. So you can download the Python package from this GitHub link and play with it and just apply it on any data you want, maybe the data from India, from Pakistan, from Bangladesh, or Philippines, wherever. Okay, so are there any questions so far? Let me check the chat. Okay, no. So, can you, yeah. Okay, so what are the statistical benefits of this approach? Well, there are two very crucial benefits. The first one is that the trajectories become independent in the limit. So this is also in physics, it's known as mean field independence or propagation of chaos. But the thing is, if things are independent, then you can write things in product form, and then it's very easy to do inference based on that. And the other thing is, because it becomes independent and we can write down individual likelihoods, we don't need to track the entire population. We can just write down likelihood function based on a random sample, thanks to a binomial randomization. Okay, some mathematical technicalities, which I won't go into the detail of. But the bottom line is, we don't need to keep track of the entire population. So, for instance, here we have this entire population, but it's virtually impossible for us to keep track of everyone. But what we can do is we take a random sample of individuals, and then we keep track of those individuals. So they, whenever they are changing their status from susceptible.
Vasu, please
Yeah.
share the presentation screen.
Huh?
Presentation screen. Please share the presentation screen.
Oh, okay. Sorry. Can you see my screen now?
Yeah.
Okay.
Mm.
Oh, sorry, I didn't realize it stopped sharing the presentation screen at some point. So, yeah. Did you guys see all this thing?
Now it's okay.
Okay. Yeah. So, yeah, as I mentioned, so it has like the statistical benefit is that you don't need to keep track of the entire population. So you just keep track of some individuals and check when they are changing their status. So, for instance, the red guys, the blue guys become red at some point. So the susceptible individuals become infected, and then at some point they also become recovered. So if I can keep track of only a handful of individuals, I can still do statistical inference based on that. Okay. The other modification, I'll very quickly talk about this, and then I'll go into some real application to COVID-19 data. This is what is known as the network model. So as I mentioned, we have this mass action approach, which was given by mainly physicists, that essentially, like for gas molecules, that an infected individual can infect anybody else in the population. Right? But this is not very realistic, especially with the lockdowns and everything. An infected individual cannot infect anybody in the whole city or in the state or so what people do is they have network models. So they say one particular type of network is called the CM graph, the configuration model. And the configuration model is nice because it allows you to describe the degree distribution. What is a degree? A degree is basically the number of connections you have. So you can say, okay, if I live in a household where there are 5 individuals, like my parents and my grandparents and my wife and some kids and so on. So those are your connections. If you go to school and then you sit in a class with 30 students, those are your connections, and so on. So it basically allows you to describe the population, and then the way it does is you specify the number of connections for each individual. So those are these little stubs, and then you uniformly at random you match them. and then that's how you create the graph, kind of like what you see here. So at random, I'm picking 2 of these edges and then matching them. That's giving me the graph. Okay, and how does the infection process work on it? So there are 2 different approaches again. So you can either assume that I've been given the network, now I'm just running the infection process on it, or you can say, okay, I'm creating the network as the infection is progressing. So you have individuals, now I have color-coded them in blue, red, and green. So the blue is susceptible, red is infected, and the green ones are removed. So the red ones, they try to infect their blue neighbors at some point, and then the blue ones become red. And then you can also drop your connection. So for instance, whenever this red in the middle, he was red, then we remove this edge. So that means that because of quarantine, for instance, he can no longer infect this one, but otherwise they were connected. So maybe they were office colleagues, for instance. Okay, so they could have been a connection and could have been a spread of infection, but because of lockdown, it's no longer possible. So that was kind of a situation. And as you can imagine, this is much more elaborate scheme. And then also there is a dynamic method where, as I mentioned, you create the graph as the disease is progressing. So initially everybody is susceptible except for a few infected individuals, and then infected individuals are going on infecting other people and they're making newer connections. And you can show that for some of the probabilistic quantities that we're interested in, these 2 constructions are essentially the same. I mean, they give you the same thing. To describe mathematically, you need to know the degree distribution. So like their connectivities, which that is described by this generating function, if you're familiar with it, and the mean degree, so mean number of connections basically. And this is a probability distribution describing the number of connections you have. And then as before, you have a contact interval and infection, and then you can also drop edges. Now I have this, of course, this is agent-based description, but if I have a large graph, meaning a large population, now moving from the microscope to the macroscope, then you can show the limiting proportion of susceptible individuals, the susceptible vertices in the graph, that can be described by this ordinary differential equation here. So it's a bit of mathematical work to arrive at this equation, but you can describe, you can get the limit, and then you have this value. So the bottom line is similar to the Kermit-McCantic equation. We can derive equations for the large graph limit, and once we do that, we can apply it to all sorts of things. So I'll briefly show you some results that we did for the state of Ohio, COVID-19. So we started the modeling activity in March, and these are, so on x-axis you have date, and on y-axis you have new infections, daily new infections. And this was the initial data. So as you saw, then this is going up and up and up, and then there is a delay, but this could be because of backfilling. So the data is not very reliable for the next or the last 2 days or so, because not all cases have been reported by that. And then, so we did some modeling, and we used this network-based model on that. And this is the kind of prediction we made. This was early on in March. As you can see, this blue curve shows what would happen under a social distancing regime, and the yellow ones show what would happen if there's no social distancing. So as you can see, of course, this is the amount of decrease that you can decrease in total cases if you do practice social distancing and lockdown and so on. But otherwise, you will just have many more people dead. Now, towards the end of March, this is what happened. So we had this exponential growth initially, and then it seems like it's decaying, which is not a good sign. And it was very puzzling, like why would that be the case? But of course, I mean, it has to do with lockdown and all, but this was, and we spent a lot of time trying to investigate what could be the reason, whether there was any geographic aspect or not. But based on that, we had to devise our estimate. So now, starting, of course, from much higher numbers, now we were predicting that we would have more or less 175,000 cases in the state of Ohio, based on data till more or less the last week of March. Now around mid-April, again, so we have this exponential growth in the beginning, and then after this March 17th, so you remember in the early picture we had a slight decline here. Now it has changed into a slight ascent. So this is no longer an exponential growth here, but it's kind of like a linear growth, but with a very small slope. And again, this is very puzzling, but of course, as I mentioned, there's a lot of human behavior that we need to take into account and so on. So this drastically changed our predictions, and then we are predicting much smaller numbers. That okay, it will be not in more than 100,000, but it will come down to actually 30,000 and so. But then again, of course, a lot of things happened, and you guys might have. I'm not sure if you have followed what was happening in the US and in the news, but here's a timeline of social distancing measures. So around March 5th, there was this Arnold Sports Festival that was cancelled, and then on March 9th, Ohio declared a state of emergency. March 12th, large gatherings were prohibited. March 15th, bars and restaurants were closed. March 17th, statewide school closure. March 18, barbershops, beauty salons were closed, and March 23rd, ODH issued stay-at-home orders. That's the complete lockdown. So this coming back from, or you have an exponential growth and then lowering that to a linear growth, it was all because of these social distancing measures. Where do we stand now? Well, now we have data till July, basically. So this is the March thing is way past. So we had an initial exponential growth and then a long linear growth phase, and then we had a decline. So we were doing so well, but then the state reopened, and then all of a sudden things are really bad. So we had an exponential growth again, and this is totally out of control. And I'm sure you might have followed the news in the for US and things. So we're not really doing that well in terms of curbing the growth. So of course, now again, this is the latest prediction that I did last week, I guess. So again, now we are back to predicting numbers in 150,000 cases. So that's the most likely curve here, the brown one here. And the green curves are kind of the confidence bounds. But as you can see, that there is a tremendous amount of uncertainty in the predictions. And part of the reason is that the human behavior is so unpredictable. So that's why we have those things. And then we have also like the mean of the predictions and the medians, and then they're all very large numbers. So this is a scary looking thing. So the bottom line is you can do predictions and things like that. We also applied this method to the whole of USA and a number of other countries with reasonable success initially, and not so much later on. I personally did some modeling for India, but I'm not showing you any of the India results here. And this plateauing thing, as I mentioned, going from exponential growth to a linear growth, this seems to be common in many places because of lockdown and others. All right, so that's the main content, and just to recap of what this has been all about, and what we can take away from this is that the first thing is, well, social distancing works. That's the bottom line. So in all forms of social distancing, you don't have to necessarily lock down, but do practice social distancing. It does break down the epidemic, and wear masks and and things like that. So it's almost undeniable. I mean, it's almost as certain as gravity, for instance. So if you drop a pen, it drops to the ground. There is no ambiguity, there is no uncertainty around that. And the same with social distancing. This method that I talked about, this dynamic survival analysis, which combines two different approaches of mathematics, so dynamical systems and survival analysis, it provides you a principled approach to parameter estimation and uncertainty quantification. The fact that we have a tremendous amount of uncertainty in our latest predictions is an honest one, right? So if you put a lot of assumptions in your model, you can be very sure about the outcome and wrong about the outcome. But if you have fewer assumptions, you can have a lot of uncertainty, but that's an honest assessment of the situation. So it's a principled approach to uncertainty quantification and so on. And then of course there's plenty of unknowns. So there's no mechanistic understanding of the plateauing, the effect of seasonality, and of course there is also a lot of biological unknowns regarding the virus itself. So and for simplicity, I described the Markovian version here, where future depends on the present, not on the past. But you can easily extend it to non-Markovian models, which is a bit more technical because you have to make use of what are known as measured value processes, things like that. But there is a standard limit theory for measured value processes that you can use to describe non-Markovian systems. So with that, I would of course acknowledge the funding. The funding, especially for me, that came from at various time points, different sources: the National Science Foundation, NSF, the National Institutes of Health, the Mathematical Biosciences Institute, and of course the Ohio State's President's Postdoctoral Scholars Program, which is supporting my stay here at the Ohio State University in Hakim Al-Hattab for the HTML slides. So with that, I would thank you for your attention. I'll be very happy to take questions if there are any.
Thank you, Vasu, for your nice presentation.
Thank you.
So now we'll go into the question answer session. So it will be conducted by our joint convener, Mr. Somu Saha. Dr. Somu Saha.
Hello.
Yeah.
Here is one question is asked in the YouTube chat. Is the mathematical model different from SIR model?
Yes, it is different in the sense that it has a network in place, and the non-Markov version can actually take into account what is known as SIR type of model or any kind of model. So it's a much more general than the standard SIR model. The standard SIR models are not very realistic in today's world, actually. It's a network-based model, and which takes into account the distancing. So it is different from the SIR model.
Okay. So another question is it possible to incorporate behavioral aspects into the configurational modeling?
Yeah, so that's a very good question. The answer is yes and no at the same time. Yes, because some of the aspects of behavioral changes can be incorporated. For instance, dropping of edges in the configuration model. So that's that's a way you can model social distancing or quarantine. So as soon as you get infected, the verdict can drop its connections, but it's not only connected with the whole people. So that aspect have been already incorporated. But there's a lot of noise.
The voice is not coming clearly. So
a lot of the behavioral changes could be incorporated, but not everything. So this is not this is not a simulation model where you can incorporate a lot of behavioral changes, but you do have some behavioral changes. For instance, dropping of ages, which is to mirror social distancing. With infected individuals, drop their connection, and
Okay. Thank you. And the linking
Soma
question
sir,
will be,
please mention the name who has asked the question.
yeah, the name was, I think, just Lanjan Chanu Athakapam.
Okay.
I think he's, yeah. And the linking question is, how do we do this mathematically? I mean, this incorporation behavioral aspects into the configuration modeling.
Yeah, that's a very good question. That's an excellent question.
Yeah.
So the thing is, if you have noticed, let me go back to my. Can you still see my slides?
Yes, yes.
Okay, so if I go back to this limiting equation, so we have a bunch of things there, as I mentioned. So this is the configuration model. So we have this drop parameter, delta, the social distancing, and
Okay.
the limit is proposed. So in the limit there, you don't see delta, but you see that beta tilde and gamma tilde, rho tilde, and delta appears in gamma tilde here. So the point here is that you cannot identify delta as a parameter, but you can identify some transformations of those parameters. So in the sense that directly we are able, from data, we can estimate beta tilde and gamma tilde and rho tilde. Let's put those parameters directly. But information, especially for recovery, if we know that, then we can also estimate delta from data. So this is the way we have been doing. So we have daily counts that we got from Ohio Department of Health, or you can also download it from New York Times GitHub site or any source. And then if you know some information about recovery, you can also estimate what has been. So this is the oh wow. So this the curve has no dropping. So this is the no dropping scenario, and the one has dropping in the configuration. This is the social distancing scenario. This is without social distancing scenario. We estimate the parameters from data. Does that answer your question?
Okay. Yeah, there is another question that is asked by MD Asghar Mansouri, and he is asking how far this mathematical modeling has helped to combat this COVID-19 cases in India.
So I have done some modeling for India. I haven't really worked with anybody in India in the sense that officials. So I will not be able to comment on that. But some of my colleagues in the US, they did have some work with the officials, I guess. So I would say that it gives you it informs the public policy making procedure, right? And you know what's going to happen, and you can test different scenarios, so that allows you to create better public health policies. So that's somebody's ceiling fan is on or something like that. Right? There's a lot of sound. Yeah. So yeah, this has definitely helped policymaking, especially for the Ohio. I mean, I've been working very close with the state government here, almost communicating with it. Health and policy making and public health intervention. Yeah.
Okay. So here is another question is asked as in Google Meet, asked by Professor Dr. Sominderman Biswas. So if by mathematical calculation there is supposed to be a decline after reaching a peak, but in the US it is not so, what will be the mathematical prediction in this regard?
Yeah, so that's a very good question. So, so the standard SIR model will say that it is going up, it will hit the peak, and then it will come down, right? But as I mentioned, the standard SIR model is not very realistic, because we as people do not adhere to the entire model. I mean, we change our behavior. People have behaved differently. So for the kinds of models with social distancing and other, it's not necessary that it has to go to a peak and then it has to necessarily come down. You can also have a second peak. So in the last plot that I was showing, not this one, this one. So this is actually the second peak that I was showing. So it starts from June 1st, not March. Not going apart from March until June. But this is actually the second peak here. So if you can incorporate a number of change points in your model where you think that people would start behaving differently, so that would make the model parameters have different values. So you can incorporate different change points in the model, and that will give you all sorts of or give you a way to explain why you have a second peak or maybe a third peak. Who knows, right? I mean, right now US is seeing a second peak, but maybe in the fall when the schools reopen and maybe it'll have another peak. So but those are like external changes that need to be taken into account when you are doing your mathematical modeling. Yeah, so your parameters need to be updated and reset to reflect those changes. Does that answer your question?
Yeah, that's very good. Yeah, that's complete this session of question answering. And thank you. And it's over to our convener.
Thank you so much, Saha. So thank you. I want to thank my beloved friend Vasu Raman for the box. Thank you for this presentation. So
Thank you for
thank you so much. And it's the end of the webinar for today's webinar. So thanks to all the participants, all the colleagues, and my beloved students. Thank you very much.
Okay.
Hope we will meet again.
Yeah, sure.
Thank you.
Bye-bye.
Bye.